welcome to this problem walkthrough. In this session, we'll explore problem number 1493, longest subarray of 1's after deleting one element. We'll break down the problem, consider different approaches, and discuss their complexities. Let's dive in. In this problem, we are given a binary array called nums, where each element is either a 0 or a 1. The task is to determine the size of the longest subarray consisting only of 1's after deleting exactly one element from the array. If the array contains no 1's at all, the output should simply be 0. For input, we have a list of integers, nums, with a length ranging between 1 and 100,000. The output is a single integer representing the length of the longest possible subarray of 1's after the deletion. This problem requires us to carefully analyze the array to find the optimal element to delete in order to maximize the length of 1's in the resulting subarray. To understand this better, let's look at an example. If the input array nums is 1, 1, 0, 1, the output should be 3. Here's why: if we delete the 0 at index 2, the array becomes 1, 1, 1, which is a continuous subarray of 1's with a length of 3. Now, consider another example where the input is 0, 1, 1, 1, 0, 1, 1, 0, 1. In this case, the output is 4. By deleting the 0 at index 4, the array transforms into 0, 1, 1, 1, 1, 1, 0, 1. The longest subarray of 1's in this modified array has a length of 4. Let's explore another example to clarify further. If the input array is 1, 1, 1, the output will be 2. This is because, regardless of which one you delete, the remaining subarray of 1's has a length of 2. For instance, deleting the first one gives 1, 1, which has a length of 2. Similarly, deleting the second or third one would also result in a subarray of length 2. These examples demonstrate how the problem is fundamentally about identifying the best element to remove in order to create the longest sequence of 1's possible. Now let's consider some constraints and edge cases. First, the array length can be as small as 1 or as large as 100,000, so our solution must be efficient. Each element in the array is either 0 or 1, which simplifies our analysis. For edge cases, if all elements are 1's, like in the array 1, 1, 1, 1, deleting any single one will leave us with a subarray of length 3, which is the array length minus 1. If all elements are 0's, such as 0, 0, 0, there are no 1's to form a subarray, so the result is 0. Finally, if the array contains only one element, like 1 or 0, deleting that element results in an empty array, meaning the output must also be 0. Understanding these examples and constraints leads to some key observations about the problem. The main insight is that deleting one element allows us to remove a 0 and effectively merge two subarrays of 1's into a longer continuous sequence. If the array contains no 0's, meaning it's already all 1's, the result will simply be the array length minus 1, because we must delete one element. To solve this problem efficiently, given the potential size of the input, we'll need to employ a sliding window approach. This method ensures we can evaluate the array in linear time, or O(n), which is critical to handling the upper limit of 100,000 elements. To tackle this problem, we explored multiple approaches. The first was a brute force method, where we simulate removing each element one at a time. For each possible removal, we calculate the length of the longest contiguous subarray of 1's. This involves iterating through the array and summing the ones to the left and right of the removed element. However, while this approach is straightforward, it's highly inefficient with a time complexity of O(n squared, since we repeat the process for each index, and each calculation requires scanning the array. The space complexity is O(1), since no additional data structures are used. Ultimately, the quadratic time complexity makes it impractical for large arrays. To improve efficiency, we then considered an optimized sliding window approach. Here, we maintain a window of 1's with at most one 0 removed. Using two pointers, left and right, we expand the window while keeping track of the number of zeros within it. If more than one 0 is encountered, we shrink the window by adjusting the left pointer until the condition is met. Throughout this process, we track the maximum window size. This method is much faster, with a time complexity of O(n), since both pointers traverse the array only once, and it requires no extra space, making it O(1) in space complexity. One major advantage of the sliding window technique is its efficiency. It operates in linear time, making it ideal for handling large input sizes. However, we also explored an alternative sliding window approach that incorporates pre-processing. This involves pre-computing the lengths of contiguous ones and identifying segments separated by single zeros. By merging these segments during a second traversal, we can calculate the maximum possible length of ones after removing one element. This pre-processing approach has a time complexity of O(n), as the array is traversed twice, once for computing segment lengths and once for merging. However, it requires additional space to store segment lengths, leading to an O(n) space complexity. While effective, this method introduces extra complexity and is less space efficient compared to the sliding window approach. After evaluating all options, we chose to proceed with the optimized sliding window approach. This method aligns perfectly with the problem's requirements, as it allows us to maintain the condition of removing at most one zero while dynamically maximizing the length of the subarray. The sliding window framework provides a natural fit for this type of problem, with its ability to adjust boundaries dynamically. Key insights include the use of a zero_count variable to track the presence of zeros within the window, which simplifies the logic and eliminates the need for redundant array scans. Notably, the result is derived by subtracting 1 from the maximum window size, as the problem requires removing one element. Comparing this to other methods, the brute force approach is too slow for large inputs, while the pre-processing method, though feasible, demands additional memory and complexity. The sliding window technique strikes the right balance between speed, simplicity, and space efficiency. The sliding window approach stands out because of its efficiency, simplicity, and optimality. With a time complexity of O(n) and a space complexity of O(1), it's well suited for handling large arrays. Its implementation is straightforward, making it easy to follow and maintain. Moreover, it directly addresses the core problem requirements without introducing unnecessary overhead, such as additional data structures or multiple traversals. By dynamically adjusting the window and leveraging the zero_count variable, we achieve a solution that is both elegant and effective. This combination of efficiency, clarity, and alignment with the problem's constraints makes the sliding window approach the ideal choice for this challenge. The problem requires us to find the longest subarray of ones possible after deleting exactly one element from a given binary array. The brute force approach is straightforward but inefficient. The intuition here is to systematically simulate removing each element, one at a time, and then calculate the length of the longest contiguous sequence of ones in the resulting array. To implement this, we start by initializing a variable max_len to keep track of the maximum length found so far. For each index in the array, we create a new array by removing the current element and traverse the modified array to count the longest streak of ones. If the current streak is larger than the previous maximum, we update max_len. Once all elements have been considered, we return the maximum length found as our result. While this approach works, it is computationally expensive and can be optimized further, as we will see next. The brute force approach has a time complexity of O(n², because for each element, we traverse the array to calculate the longest streak of ones. Additionally, the space complexity is O(n), since we create a new temporary array for each iteration. To optimize this, we can skip creating new arrays altogether and calculate the result more efficiently by focusing on the segments of ones around each zero in the original array. The idea is to track the streaks of ones before and after each zero, allowing us to calculate the potential maximum length directly. To do this, we maintain three variables: max_len to store the maximum length found, prev_ones to track the length of the previous segment of ones, and cur_ones to count the current streak of ones. As we iterate through the array, we increment cur_ones for each one encountered. When we hit a zero, we calculate the potential maximum length as the sum of prev_ones and cur_ones, update max_len if necessary, and then update prev_ones to the value of cur_ones before resetting cur_ones. This way, we efficiently account for the impact of removing a single zero. Finally, we handle edge cases, such as when there are number zeros in the array, and ensure the last streak of ones is considered after the loop. This optimized approach reduces the time complexity to O(n) and the space complexity to O(1). The key insight behind the optimized approach lies in recognizing that the problem can be reduced to merging two segments of ones separated by a single zero. By removing the 0, we effectively combine the two segments into a longer one. This is why we focus on tracking the streaks of 1's on either side of each 0. Additionally, we need to handle edge cases gracefully. If the array contains number zeros, the result is the total number of 1's minus 1, as we must delete exactly one element. On the other hand, if the array consists entirely of zeros, the result is simply 0, since no subarray of 1's exists. What makes the optimized approach powerful is that we don't need to recalculate the streaks of 1's from scratch for every element. Instead, by maintaining running counts of preb_1's and cur_1's, we achieve linear time complexity while ensuring correctness. The optimized algorithm relies on three key variables: preb_1's, cur_1's, and max_len. Preb_1's keeps track of the length of the last segment of 1's before encountering a 0, while cur_1's records the current streak of 1's. Max_len is used to store the maximum subarray length found throughout the process. These variables work together to efficiently calculate the potential merged length of 1's without having to recompute the streaks for every 0 encountered. This design reduces the time complexity from O(n)² in the brute force approach to O(n) in the optimized approach. Furthermore, the space complexity is reduced to O(1), since we only use a few variables, making the algorithm highly efficient and scalable for large input arrays. Let's walk through an example to solidify our understanding. Consider the input array nums equals 1, 1, 0, 1, 1, 1. We start by initializing preb_1's equals 0, cur_1's equals 0, and max_len equals 0. As we traverse the array, we first encounter indices 0 and 1, both of which are 1's, so we increment cur_1's to 2. At index 2, we hit a 0. Here, we calculate the potential maximum length as preb_1's plus cur_1's, which is 0 plus 2 equals 2, and update max_len to 2. We then set preb_1's to the current value of cur_1's, which is 2, and reset cur_1's to 0. Continuing the traversal, indices 3 to 5 are all 1's, so we increment cur_1's to 3. After finishing the loop, we perform a final update to max_len, calculating preb_1's plus cur_1's as 2 plus 3 equals 5 and setting max_len to 5. The result is 5, which represents the length of the longest subarray of 1's that can be achieved by removing a single element. This Python implementation solves the LeetCode problem number 1493, longest subarray of 1's after deleting one element using an efficient sliding window approach. Here's a detailed explanation. The function longest subarray receives a binary list nums. The goal is to find the length of the longest contiguous subarray of 1's that can be formed by removing exactly one element. The sliding window strategy is used to achieve this efficiently. 1. Initialization. The variables n, max_len, left, and 0_count are initialized. N stores the length of the input list. Max_len tracks the maximum length of the desired subarray found so far. Left is the left pointer of the sliding window. 0_count counts the number of zeros in the current window. 2. Iterating through the array. The right pointer of the sliding window iterates through the array using a for loop. If the current element, nums, right, is 0, 0_count is increment. 3. Maintaining the window. When the number of zeros in the window exceeds 1, the while loop is triggered to shrink the window from the left. Each time the left pointer moves, it checks whether the element being excluded is a 0, and if so, decrements 0_count. For updating the maximum length, at each step, the length of the current window, excluding one element, is calculated as right-left, and max_len is updated to hold the maximum value. 5. Returning the result. Finally, max_len is returned, representing the length of the longest subarray of 1's after deleting one element. This solution effectively handles edge cases such as arrays consisting entirely of 1's, arrays with only one 0, arrays with all zeros. The time complexity of this algorithm is O(n), where n is the length of the input list, as each element is processed at most twice, once by the right pointer and once by the left pointer. The space complexity is O(1), since no additional data structures are used beyond scalar variables. This makes the solution efficient and well suited for large inputs. This is the Java implementation of LeetCode problem number 1493, longest subarray of 1's after deleting one element. The logic mirrors the Python solution with adjustments for Java syntax, including explicit type declarations and usage of Java's math library for maximum calculation. The code uses a sliding window approach to efficiently track the longest subarray of 1's after removing one element, ensuring O(n) time complexity. To solve the problem, we start with the array nums equals 1, 1, 0, 1, 1, 1, and initialize some variables. The length of the array, n, is 6, and we set max_len to 0 to track the maximum subarray length. We also initialize left to 0, which acts as the left boundary of our sliding window, and 0_count to 0 to keep track of the number of zeros in the window. Now, as we iterate over the array, the right pointer starts at index 0. At this position, nums 0 is 1, so 0_count remains unchanged. The current subarray length is calculated as right-left, which is 0. Taking the maximum of the current max_len and this length, the max_len remains 0. Moving to the next index, nums 1 is also 1, so 0_count still doesn't change. The subarray length becomes 1 and 0 equals 1, updating max_len to 1. At index 2, we encounter a 0, so we increment 0_count by 1, making it 1. The subarray length is now 2, 0 equals 2, and max_len becomes 2. Next, the right pointer moves to index 3, where nums 3 is 1. Since this is not a 0, there's no change to 0_count. The subarray length becomes 3, 0 equals 3, and max_len updates to 3. At index 4, nums 4 is also 1, so again, 0_count stays the same. The subarray length now is 4, 0 equals 4, and max_len increases to 4. Finally, at index 5, nums 5 is 1, so the subarray length grows to 5, 0 equals 5, and max_len becomes 5. Since the problem requires the length of the longest subarray of 1's after deleting one element, we subtract 1 from max_len to account for the single mandatory deletion. Therefore, the final output for this example is max_len 1 equals 4. Now let's look at another example where nums equals 0, 1, 1, 0, 1, 1, 1, 0. We start by initializing the variables, n equals 8, max_len equals 0, left equals 0, and 0_count equals 0. At index 0, nums 0 is 0, so we increment 0_count by 1, making it 1. The subarray length is 0, 0 equals 0, so max_len remains 0. At index 1, nums 1 is 1, so 0_count doesn't change. The subarray length is 1 and 0 equals 1, and max_len updates to 1. At index 2, nums 2 is also 1, so 0_count stays the same. The subarray length becomes 2, 0 equals 2, and max_len is updated to 2. At index 3, nums 3 is 0. Here, we increment 0_count to 2. Since we are only allowed one 0 within our window, we shrink the window by moving the left pointer forward until the 0_count decreases back to 1. We achieve this by moving left to 1 and decrementing 0_count to 1. After adjusting the window, the subarray length is recalculated as 3, 1 equals 2, so max_len remains 2. At index 4, nums 4 is 1, so 0_count doesn't change. The subarray length becomes 4, 1 equals 3, and max_len updates to 3. At index 5, nums 5 is 1, keeping 0_count unchanged. The subarray length is 5, 1 equals 4, and max_len becomes 4. Similarly, at index 6, nums 6 is 1, so the subarray length increases to 6, 1 equals 5, and max_len updates to 5. Finally, at index 7, nums 7 is 0, so we increment 0_count to 2. To maintain only one 0 in the window, we adjust the left pointer. The value at nums left is 1, so we simply move left to 2, ensuring 0_count is reduced back to 1. The subarray length is then calculated as 7, 2 equals 5, so max_len remains 5. Subtracting 1 for the required deletion, the final output is max_len 1 equals 4. For another example, consider nums equals 1, 1, 1, 1, 1. Here, the array contains no zeros, so the entire array is already valid. We initialize n equals 5, max underscore len equals 0, left equals 0, and 0 underscore count equals 0. As we iterate, no zeros are encountered, and the subarray length increases at each step. At the end, the maximum subarray length is 4, and subtracting 1 gives the final output as 4. The time complexity of our solution is O(n), where n represents the length of the input array nums. Let's break this down step by step. First, the outer for loop iterates through the array using the right pointer. Since this pointer traverses each element exactly once, it contributes O(n) to the overall complexity. Next, we have the while loop that is triggered whenever the 0 underscore count exceeds 1. At this point, the left pointer moves forward to shrink the window, ensuring that 0 underscore count returns to 1. Importantly, the left pointer will also traverse each element of the array at most once throughout the algorithm's execution. The way the left and right pointers progress ensures that their combined movement is limited to O(n). Lastly, other operations, such as checking if nums right equals 0 or updating variables like max underscore len and 0 underscore count, are constant time operations O(1) performed during each iteration. These operations are negligible in comparison to the O(n) contributions of the loops. When we combine the contributions of the for loop, which is O(n), with the amortized cost of the while loop, which is also O(n), the total time complexity becomes O(n) plus O(n), simplifying to O(n). Now, let's examine the space complexity. The space complexity for this solution is O(1), which means the algorithm uses constant extra space regardless of the input size. Breaking this down, the input array nums itself is not modified, and no additional space is allocated for it. While the array does occupy O(n) space in memory, this does not count as extra space used by the algorithm. The only memory used by the algorithm comes from a fixed number of variables, including n, max underscore len, left, 0 underscore count, and right. These variables require constant space, O(1). Since no additional data structures, such as arrays or hash maps, are introduced, the extra space complexity remains constant at O(1). Let's compare this optimized sliding window approach to a brute force method. A naive solution would involve generating all possible subarrays, counting the number of 1's in each subarray, and ensuring that exactly 1 0 is removed. Generating all subarrays has a time complexity of O(n squared, and for each subarray, counting the 1's and checking the conditions would take an additional O(n) time. This results in a total time complexity of O(n cubed for the naive approach. In contrast, the optimized sliding window method avoids generating subarrays entirely. By using two pointers to maintain a dynamic window and track the required conditions, it achieves a linear time complexity of O(n). Additionally, this approach avoids any extra space overhead required for storing temporary subarrays. The sliding window ensures both pointers traverse the array at most once. There's no backtracking or redundant steps, which reinforces that the total number of operations is proportional to the size of the input, n. Furthermore, the constant number of variables used guarantees an extra space complexity of O(1). Now let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, the input array contains no zeros. In this situation, the while loop never executes, and the algorithm simply iterates through the array once using the for loop, resulting in O(n) time complexity. For the average case, the input contains some zeros. Here, both the left and right pointers traverse the array, ensuring the time complexity remains O(n). In the worst case, the input consists entirely of zeros. In this scenario, the left pointer moves forward for every 0 encountered, but the total traversal of both pointers is still bounded by O(n). Across all cases, whether best, average, or worst, the time complexity is consistently O(n), and the space complexity remains O(1), since only a fixed set of variables is used, with no additional space required for data structures. One of the most common pitfalls in solving this problem is not handling edge cases properly. Consider scenarios where the array is composed entirely of 1's or zeros. If there are no zeros, the solution is simply the length of the array since no deletion is needed. On the other hand, if all elements are zeros, the solution should correctly return 0 because no valid subarray of 1's exists. Overlooking these cases can cause your solution to break or yield incorrect results, especially when removing an element isn't feasible. Another mistake arises with errors in adjusting the sliding window. If the window isn't shrunk correctly when constraints are violated, such as when more than one zero is included, it can lead to incorrect results or even infinite loops. Lastly, it's important not to confuse the sliding window technique with a fixed window size. The sliding window here is dynamic, expanding and contracting based on the problem constraints. Treating it as fixed can cause the logic to fail and produce incorrect outcomes. Another misstep is relying on a brute force approach without optimization. For example, iterating over all possible subarrays, deleting one element, and then calculating the length may seem straightforward, but it's computationally expensive. This approach can lead to a time complexity of n cubed, or worse, making it impractical for larger inputs like n equals 100,000. A more subtle but equally problematic error is off-by-one mistakes in calculations. For instance, forgetting to account for the deletion of one zero when determining the longest subarray length can skew the result. These small miscalculations often lead to suboptimal solutions or even completely incorrect outputs, so attention to detail is vital when implementing the solution. In interviews, this problem is often a test of recognizing the sliding window pattern. Sliding windows are highly effective for problems that involve finding the longest subarray or working within specific constraints. A strong understanding of this pattern is essential. Interviewers also frequently expect candidates to discuss the trade-offs between brute force and optimized solutions. Brute force approaches, while simple, are computationally expensive, whereas optimized methods like sliding window reduce the time complexity to n. Another key aspect is handling dynamic constraints, such as deleting one element. Candidates should clarify these constraints with the interviewer to ensure their understanding is correct. Finally, testing edge cases is critical. Interviewers may challenge you with arrays that have only one element, all ones, all zeros, or cases where no element can be deleted. Verifying your solution against these ensures robustness and demonstrates thoroughness. There are several related problems that share similarities with this one, which can help deepen your understanding of the sliding window technique. For example, LeetCode 1004, max consecutive ones 3, is a similar problem that asks you to find the longest subarray of ones but allows flipping up to k zeros. Another example is LeetCode 424, longest repeating character replacement, which generalizes the sliding window pattern and involves replacing characters within a constraint. The exact problem we're discussing, LeetCode 1493, focuses on deleting one element to maximize the length of ones. Lastly, LeetCode 485, max consecutive ones, is a simpler version of this problem where no deletions are required. Studying these related problems can help you recognize patterns and adapt your approach to variations of the sliding window technique. When exploring alternative approaches, it's essential to understand the trade-offs involved. A brute force approach, which examines all subarrays, deletes one element, and calculates the resulting lengths, has a time complexity of n cubed. While straightforward to implement, it becomes computationally prohibitive for larger input sizes, making it suitable only for small datasets with n less than 100. The sliding window approach, on the other hand, is far more efficient with a complexity of n. By maintaining a dynamic window of valid subarrays and allowing the deletion of at most 1 0, this method is ideal for large inputs but requires careful attention to managing the window size dynamically. Another option is the prefix sum approach, which also has a time complexity of n. This method involves pre-computing sums to facilitate subarray calculations. While effective for certain variations, it typically requires more memory than the sliding window, making it less space efficient. The two-pass approach is another efficient alternative worth considering. In the first pass, you calculate the maximum length of subarrays of ones that are separated by zeros. Then, in the second pass, you combine these results to determine the overall longest subarray after deleting one element. This approach has a time complexity of n, which makes it efficient for larger inputs. It is particularly useful when simplicity in implementation is desired, as it avoids some of the complexities associated with dynamically managing a sliding window. However, it may require additional space to store intermediate results, which can be a trade-off depending on the constraints of the problem. Great job! In summary, we used the sliding window approach to efficiently solve this problem with a time complexity of n. Remember to practice similar problems to strengthen your understanding of contiguous subarray techniques. Thanks for watching, and don't forget to subscribe for more coding walkthroughs. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!